I was cycling, I'm like, ugh, it's very hard to cycle, and then I could hear a problem, and then I got off the bike and I could see, oh, no air. Okay, let's continue. Where is Gao?
I don't know. We don't know.
We don't know?
No one knows.
No one knows.
Yeah.
She didn't send you a message.
No. Like me.
We miss her.
Like you, yeah. I don't miss her. Maybe she's sick. Or maybe she's asleep.
Yeah, I think.
Yeah.
But nowadays,
She's sick.
Sick.
Yeah, because you remember the last week. She felt very terrible.
Yeah, I remember. Oh, we'll continue. Okay, induction. Induction, yeah. Not introduction. Very different meaning to introduction.
Could you explain?
Yeah, the whole lesson is about it. I'll explain. So, we've seen that moving a charge in a magnetic field will experience a force. What happens if we move the magnetic field? So, look at this little picture here. Okay, simple picture. You've got voltmeter, and you've got a wire around here into the voltmeter, and you have a magnet. And you move the magnet, you get a voltage. You move the magnet out, you get a voltage. You don't move the magnet, no voltage. So only when the magnet is moving will it make a voltage. And this is called electromagnetic induction. This is what we mean when we say induction. This process of making a voltage
Oh.
while the magnetic field is moving, a voltage will appear. That's called induction. Do I want you to draw this?
Easy,
Yeah.
Easy.
Yeah, you should draw this. It's good for you.
Just voltmeter and easy.
That's beautiful, Dan.
Small. Very small.
Oh, it's different.
Yeah.
In Wednesday we will do the export all day.
Experiment.
Ah,
No,
yes.
not the whole day.
Oh, how long? Maybe in the morning we can finish. Oh,
It depends.
it depends on what.
Depends on how good you are.
We are the best.
Are you? Are you?
Yes.
What's your attendance at?
What's standard?
What's your attendance percent? 79?
Who knows? Who knows?
Who knows? Indeed, who knows?
Yeah, but maybe now is 80.
Ah,
Maybe now is 80.
so now you're the best.
Why?
Because now you're 80.
But the others is better than me. It's good than me.
We try the.
They come to school more than you.
Yeah.
Alright, let's continue. So, the definition is electromagnetic induction is the production of an EMF across a conductor exposed to a time varying magnetic field. There's a lot of words here. Induction is when you make a voltage in a conductor because you change the magnetic field. That's what it means. I'll say that again. Induction is when you make a voltage in a conductor because you change the magnetic field. Change the magnet. Do you understand? So this is the definition. You can write that down. Be strong, Summer. Got that? Yeah? Okay. Good job. Right. Alright, let's see. So we have two laws about induction. The first law is called Lenzs Law. Wait, don't write it down yet, because I need to explain with a picture. If the induced current flows, the direction is always such that it will oppose the change which produced it. So let me explain this picture. Okay? The magnet goes in here and the current comes out. Current comes out. So the magnet goes in, magnetic field goes in, and the current comes out. Here, the magnetic field comes out and the current goes in. So I know this goes in and the current goes to the right, but really we say the current goes to the left up here. Okay? So magnet in, current out. Magnet out, current in. This is what we mean when we say oppose. Okay? It's opposite. You understand? Yes? You understand or you don't understand? Yeah? Magnet in, current out. Magnet out, current in. That's Lenzs Law. You look confused.
So
what? So that's Lenzs Law.
what's
It's a great law. Simple law. Magnet in, current out. Magnet out, current in.
so what we can get?
What we can get.
Yeah.
So if I say to you, we put the magnet in,
Yeah.
which way will the current go? You say
Out.
out. Yeah, good. Yeah, Lenzs Law.
Just this.
Just this. Yeah, that's all. Yeah, okay.
Okay.
You can write this down now.
So
Simple law.
we need to draw.
No, it's okay.
Okay.
But you should write the law down.
If we change the magnet.
Oh, yeah, then it's opposite.
What?
So, you mean like if you put S here
Yeah.
and N here? Oh, Ben, it's confusing me. I would imagine
Oh. Just opposite. Maybe.
opposite, yeah.
I don't know.
I would hope.
You never think about this.
No. I don't worry about this.
Okay.
Um,
Okay, I don't know. So,
no, Ben, maybe it's the same. I don't know. I'll have to, do you know what? I'll have to check it. I don't know, Ben. Now you confused me. Ben is a confusing student. It's good. It's good. Okay, continue. So far we know if you move a magnet, you'll get a current. Great. And we also know the direction is opposite. Great. But what we don't know is the voltage. How much voltage we have. So we have a way to calculate the voltage called Faraday's Law. Now this formula is a little bit confusing. Faraday said the voltage, the EMF, is equal to minus N, change in flux over change in time. And the only reason for the minus is Lenz's law, meaning opposite. Okay? So if I go back to the picture for a second, what we don't know is the voltage.
it is N meter.
This one is well, you can use a voltmeter or an ammeter, doesn't matter.
But if we use voltmeter.
For Faraday's law, it's a voltmeter. Yeah. Faraday can tell us the volts.
Oh.
So Faraday said, this is the formula for calculating the volts.
Oh.
It's the change in the flux over the time multiplied by minus N. But the minus is only for the direction. So if the magnet goes in, the voltage comes out. That's the only reason for the minus.
EMF.
Yeah.
Is volt.
Oh, Ben!
Oh, I know. I
Okay.
remember.
Okay.
Yesterday it's the small volt
Yeah. In the battery.
battery. Yeah.
Yeah. Okay, break this down.
Holding on.
No, just the box. You writing his name down? Yeah, Faraday. Doomsday? No, Faraday.
Superman.
Yeah, no, I know Doomsday.
Yeah.
What's
He killed Superman.
Yeah.
You know Superman?
Superman? Yeah.
Yeah. Doomsday killed Superman.
Oh, I don't know.
You don't know this? Everybody knows this.
You sent me.
You got that? I think you should write down as well that the minus is for Lenz's law.
Minus.
You know minus, don't you?
What happened to you today?
Yeah, it's a good question, Summer. It's a good
I think
question.
I never see the minus
The word, yeah, okay.
but I also say minus.
Yeah.
It's my first time.
It's your first time seeing the word minus. Great. Well, how do you spell plus?
Plus.
Mm-hmm.
TLUS. I say 6 plus.
Yep.
iPhone 6.
iPhone 6. True. That is true. There's no iPhone 6 minus. Right. Continue. You got that?
Yeah.
Okay. So, if we move a magnetic field around a conductor or a conductor around the field, can we use this to generate power? Yes, we can. We have the AC generator. AC generator It looks a little bit like what?
DC motor.
Looks like a DC motor. But there's a bit different, okay? So, in the AC generator, what you do is you turn the wheel, okay? So, you take the motor and you turn it,
Oh.
okay? And as you turn it, you get a current.
Oh, so.
So, you can power a resistor, like on your bicycle, the light.
Oh.
Yeah. Yeah. Now there's one difference between the DC motor and the AC generator, and the big difference is there's no commuter. Instead of the commuter, you have slip rings.
Why?
It's complicated. Okay, but the reason.
But you say it's separate, but I think it has some connect.
Here
Yeah.
or the last one?
Yeah.
No, it's a little bit different here. These are okay. So the last one, the last one, the commuters were like this,
Oh.
not touching. Whereas this one is like this, two circles,
Oh,
one in front of the other, not touching.
Not touch.
Yeah.
But it has some lens. I saw the
Brush is
gray.
This is the brush.
The gray.
Here,
Yeah. What? Gray lens.
this grey,
The green line.
Green.
Green.
grey, green, this one,
Green.
this one.
Yeah.
Yeah.
Connect to the.
Oh yes, connected. So the reason you don't have this one is because for the AC generator, it must be connected with the wire. So if you have just one piece with the wire, then they can turn together. Okay, but if you have it like this with the wire, you have a wire here, you have a wire here, what would happen when it turns? It would twist up, wouldn't it? Yeah. Whereas here, what they do is you put one wire through the first circle and connects on the second circle, and this turns around. And here you have one wire and it connects to the first circle. Okay. And this is a brush and this is a brush. And what happens is, as you turn this, you get a current. It comes out the first ring, along in the second ring, and then back in.
Can we just save this current?
Yes, you could put it in a battery. Correct, yeah. Yeah. So here you can put a battery, you can charge a battery, something like this. This is sometimes what happens on the electric bicycle or the electric car, you know.
Some toys.
Or some toys, yeah. If the bicycle goes downhill, then it generates power in the battery for later. This is the AC generator. Now what's interesting, if we look at this, the flux here is equal to BA. Let's not worry about the minus N, just forget about the minus N, okay? This is BA. Now what's changing here, the B or the A? Well, is the A changing? No.
No.
Only the B is changing. Okay, so fine. How does the BA change? Well, if you remember that it's changing because the angle is changing.
Oh yes.
So instead of BA, it changes because it's BA cos theta. So we have this formula.
Yes.
The BA is constant.
Yeah.
So really we just need to know how the cos changes. Well, that's sine. Let me show you.
Well, that's
Watch. So V equals this over this,
Yeah.
which equals this over this, which equals A change in, oh no, actually I leave it like this. But this changes because of the angle. So it's BA cos theta over T. Because this guy is changing. Yeah? Now, does this change? No. Does this change? No. Does this change? Yes. So you get this. Now you know this from maths. Yeah. What is this? What is this? Ah, you know this.
Sine.
Sine.
Really?
You could change this to this, Ben. Which is the same as this. This is the same as this. Ah, you did this in maths class.
Well, what's the
You did this in-
cos WT?
You know that this and this are the same, nearly.
Yeah.
Yeah?
So what's the WT?
Oh, because the theta changes.
Oh,
But we'll move to.
so just
Here is in integrate
Derivative.
derivative,
Yeah.
but
Yeah.
different for here.
Yeah, but they're nearly the same.
yeah.
Okay.
If this is small, they're nearly the same. Anyways, what is the derivative of cos?
Implies.
Sine. So this is BA sine. The voltage. So what I'm trying to say is you can have this picture. Wait. In the beginning, when the armature is vertical, you get no voltage. Then as it turns 90 degrees, you get voltage, and then 180 you get no voltage, and then 270 you get voltage, but the other direction. And then back at the beginning, no voltage. The voltage goes up, down, up, down, up, down. As this wheel is turning, the voltage here is going left, right, left, right, left, right.
Oh.
That's what's happening here. This voltage here, we think it's coming out. It's not. It's coming out and goes in. It comes out, it goes in. This is called AC.
Oh. So DC and AC is different.
Yeah. And the AC is what they use to make electricity in the power company. So somewhere in Ireland, there's a big one of these.
Oh, the wind.
And the wind maybe is turning this.
Oh.
And it makes the AC current. The AC current goes in, out, in, out, in, out. Yeah? Does anybody know how quickly the current changes? How many times per second? No? It says it on your plug. You got a plug? Like, have you got your charger? It might be on the plug.
It's Chinese.
Do you have the plug that you put in the wall?
Outflow.
What's
Like this.
Yeah, but it doesn't say it.
Yeah.
No, guys, do none of you have a plug?
The head.
The head, yeah.
input,
No, look,
output,
look,
max put?
look here.
Wait. What?
Here. 50 hertz.
50 hertz.
No hertz.
No hertz, okay.
You
Just amps. Okay. Well, anyways, Summer,
Yeah.
Can you see here? It says
Well,
50 hertz.
no, less than.
50 hertz.
Yeah.
50 or 60 hertz.
Yeah. I saw that, but
So what happens? Look. 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 These two guys here. Current goes in and goes out. Then it goes in here and out here. It keeps swapping.
Okay.
50 times per second.
oh, that's slowly. I think.
No, I don't think so.
15 times per second.
Yeah. It switches. Like this, yeah. It's not DC. DC means just one current.
Like battery.
Like battery,
I
correct.
think this is.
It is DC, yeah.
So why we say the AC?
Why AC?
why we?
It's because it's easier to make AC than DC.
But what's the difference DC and AC?
Yeah, okay.
We use because we can use the AC to charge. We can use.
Yeah, no, I understand. Okay, so two differences. AC, DC. So the AC, it has a frequency of 50 hertz, where DC it doesn't, it's constant. Okay? The AC, you know, it travels in to your home. Here's your home. Here's the AC. It loses, it's very inefficient. A lot of energy is lost. I think maybe it's like 50%. Yeah. Whereas in your home, maybe here's your battery, and you have it into your phone. So here, this is DC. I'm not sure. It's quite good. Maybe it's like 90%.
Oh.
Okay. But here's a difference here. To make AC, that's cheap.
Oh.
To make DC, that's not so cheap. So what usually happens is you have your wind turbine. This makes AC. It sends your AC to your home, and then here it can maybe be changed into DC.
Oh.
So, for example, maybe you have something like this, changes it from AC to DC, or something like this, AC to DC. Not everything in your home needs DC. For example, the lights, they can use AC. They don't need to use DC. Okay. Electric kettle, washing machine, oven, microwave, these can all use AC. TV, fridge I think would be AC. TV would be needing DC.
There's some fridge that are heavy.
Yeah, but I think the fridge can use AC, at least the older fridges anyways. Basically, you usually need DC for electronics, like phone, TV, computer. But big items like light, fridge, oven, microwave, heater, they can use AC. Okay, so another thing is AC is good when you have a lot of current, like maybe 10 amps. But DC is really good when you have a small current, like 1 amp. Advantages and disadvantages.
Okay.
Yeah. Right, so you need to draw this. And then you'll need to draw this. Yeah. Yep. Yeah.
The red and blue is connect or
Yeah.
connect?
Yeah.
Art.
You mean it's this?
Yeah.
Why the?
Well, no, it's connected, Ben, yeah, but there's a wire on it. Can you see? The only reason for this is so you can turn it.
Oh.
But the current is in this green wire that goes around it. It's like this. You have this, and then you have a wire which is on it. So the reason for this is so you can turn it, because if you had only the wire, you can't turn that.
How to say that art becomes from the daily life.
Art from life, is it?
Yeah, it's this.
Yeah.
The current is this way.
In this picture?
Yeah.
In this picture, oops, the current is, yeah, this way. Up, across, down.
But you say it's
What?
no change.
Oh, yeah, so, no, well, this current is going up, okay? But when it comes over to here, it's going down. And it's going a different, okay, maybe we can draw this, okay. So, in this picture, the current is going up, down, in here, and out. Now, when the blue piece gets over here, the current is going down, down, oh, hang on.
I don't know why you say.
I understand. Here the current is going up. Here the current is going up. Here is going down. Huh? Yeah, I get what you're saying, Ben.
My question just
It says it changed direction, yeah.
it will. I mean, it's here. I don't know.
你想说啥？
Yeah, you're right, Ben. I'm confused now. No, it does change direction, but it does. No.
But why the current will change? You say you will after.
Yeah. No, I know.
Yes, I say the current is.
Yeah, no, I understand, Ben. I understand. Okay, I'll try. I'll try my best. Maybe I need to use this. Okay, so here's the armature, right? This is the blue piece, and this is the red piece. Okay, so right now, the current is going up. So this wheel here, the current is going in, because this one's going up. Okay. Now, if I move that over to here, that means this is still going down, this is still going up.
And change.
But this one here is the red one. So, not the blue one, it's the red one. And the red one goes into the first one. It's hard, can you... maybe I need your... Yeah, give me your hands.
Yeah.
Right. Put one hand... Give the other hand, right. Put them... Right, I want them like this. Okay, good. Right. Now, this one here... This is the blue one, and the blue one goes into... The blue one goes into the one further away. Okay, so this one goes in here, and the current is going in. So this one, the current is going in. Okay.
It is going in.
This one is the blue one,
Okay.
and the current, the blue one goes to this guy, and the current is going in. Yes? Okay. So this one is connected here. So when this turns, this one is still connected here, and this one is still connected here. But this guy is now going the other way because it's on the other side. Here it was going in and here it's going out. So if this one is going the other way, it must mean that this one is also the other way. Yeah? It's confusing, I know.
The second one is connected to the blue one. And
The blue one
yeah.
is connected here.
Yeah.
The red one here, and they
Yeah,
never
and
change.
Never change.
Never change.
If you move the blue.
Yeah, if the blue guy is over
Yeah,
here,
yeah.
it's still connected to this.
Yeah.
But when the blue moves over here, you see, this changes.
And you get the opposite.
And you get the opposite
But
direction.
in my opinion,
Go on.
you will how to say?
Yeah?
Disappear.
No. Good opinion, but no. The current is always up and always down, and the blue is always here, and the red half is always here. So when this turns upside down, the current changes direction in the blue guy, so it must change here. Yeah. Is it okay? You're not happy, I know, I'm sorry.
And the second picture,
You ready for the second picture? Ah, there's no names on it.
magnets and brush.
Yeah, but these are called slip rings.
AC.
X, H.
And the name of this, Ben, is an AC generator.
Oh.
Yeah, that's important.
Second picture.
We'll get to it. You know, sorry.
It's S, H,
S-L-I-P.
L.
S-L-I-P, slip rings.
L-I-P.
Yeah, slip rings.
Okay.
We will draw this in.
Maybe, yes.
What?
Yes. Mm-hmm. Okay.
And the formula.
No, don't need that, no.
Don't need.
I was trying to explain why you get this picture, because it's sine. Now wait, you must draw these positions as well in the exam. They want to see the graph with the positions of the armatures.
Oh.
Now, what the heck? Wow. Amazing. Okay?
Okay.
You got that?
Yeah.
The voltage increases and decreases.
In cancel.
Ah, now I know what you mean. No, it doesn't cancel. Yeah, I understand what you mean now. I give you an example, okay? So, Summer, come here.
Yeah. Okay.
Right,
What?
so, if I hit him on the left, and then the right, and then the left, and then the right, does that cancel? Does he feel the pain? Yes. So, it's the same idea, Ben. The voltage moves left and right, you can still do work. You can still do work.
Well, how about the current move?
Yeah, also left and right.
What? Left, right.
Yeah.
Mm-mm. Strange.
It's strange, yeah. It is strange. So, I think we have a formula now. Alternating current is when the flow changes, whereas a DC current is the flow is one direction. Now, Summer,
Yeah.
the AC current goes from minus to a plus, and it has an average voltage. So I'll explain here with a graph, okay? So here's time AC. It goes up, down, like that, okay? And here you have a max, and here you have minus max. You know, like 200 minus 200, okay? This is what a DC does. DC just is constant current. And then we can say that this one is kind of like this one if we use this formula. This here we call it V average. And the V average is the V max over root 2. So, for example, imagine that this is 300 and this is minus 300. You were saying this is like 0, but it's not. Really, it's like 212.
Oh.
So it cancels, like, we lose a little bit, but, you know, it's 212. Well, I think you can write this down. And then once you write these two boxes down, we'll finish for now.
Also.
Hmm?
All.
Yes, write down both boxes and then we'll finish.
What's the both box?
Write this down, go for lunch.
Oh. Lunch.
Yeah, look how quickly Summer's writing.
Hungry. So how long we will finish the expo?
Oh my goodness, okay. We'll talk tomorrow about it. You're so Summer.
No, you will get a good rest and we will get a good rest if we finish it fast.
Yeah, I know this. Did you finish your plan?
Yeah.
You have the plan finished?
Yeah.
Okay.
Oh, yes.
Plan?
To make a plan for the experiment on Wednesday.
We should be on once.
Were you in this class? Only the two of you. Gail missed it as well.
But go maybe finish it.
Okay.
Shaking. Well, last Friday, shaking. Yeah, I think. Shaking.
She was here last Friday?
Yeah, last Friday
Okay.
she was here.
You need to catch those notes that you missed. Oh no. Next lesson you'll find out.
Okay. If we can finish in the morning and we will be free in the afternoon. Yes?
That's my plan.
Oh.
Maybe we'll start.
10.
Yeah, maybe we'll start at 10.
Oh.
10?
10 a.m. We'll start at 10 a.m.
Why it's 9? It's not 9.
We'll
Maybe
start at 10
9.
and we'll try to finish at about 1.
If we started at 9,
Yeah,
we can finish in 12.
that's true.
Yeah.
But it's hard to.
But it's hard to be awake at 9,
Yeah.
isn't it?
For you, I think it's very easy. For me, maybe
Yeah.
I will be
Just,
sleepy.
just only convenient for you.
No. Wait, I think I can. I think I can. If I can't, I can
No.
drink. I can drink coffee. Yeah.
No, we'll just start at 10. It's just less stressful.
Okay.
You know, you can have some breakfast, you can relax.
Just relax.
Yeah.
So come to be for one.
Yeah.
Okay.
But we'll talk tomorrow about it, okay?
Okay.
Go